Welcome you all. Myself Nagarajan, Assistant Professor in Department of ECIT, Rohini College of Engineering and Technology. In this video, let us see the optical communication second unit topic, scattering losses. So scattering losses, on completion of this video, the student will be able to understand the scattering losses and Rayleigh scattering losses and Mie scattering. This is a type of scattering losses, non-linear scattering losses. Let us see the scattering losses. Scattering losses in fiber exist due to various factors. First one is a microscopic variation in density of fiber material, compositional fluctuations, and structural inhomogeneity. A structural defect in fiber. And this is the scattering losses are classified into two types. One is a linear scattering losses, another one is a non-linear scattering losses. In linear scattering losses, first one is a Rayleigh scattering, second one is a Mie scattering. In non-linear scattering losses, stimulated Beryllium scattering, and next one is stimulated Raman scattering. Let us see the one by one. First one is a Rayleigh scattering losses. Scattering losses exist in optical fibers because of microscopic variations in the material density and compositions. As glass is composed by randomly connected network of molecules and several oxides, these are the major cause of compositional structural fluctuations. These two effects result to variation in refractive index and Rayleigh type scattering of light. Rayleigh scattering of light is due to small localized changes in the refractive index of the core and clad materials. So Rayleigh scattering losses, there are two causes during the manufacture of fibers. One is first is due to the slight fluctuations in mixing of ingredients. The random changes because of this are impossible to eliminate completely. And second one is the other causes is slightly change in density as the silica cools and solids. When light rays strike such zones, it gets scattered in all directions. The amount of scatter depends on the size of the discontinuity compared with the wavelength of the light, so the shortest wavelength suffers most scattering. Scattering loss for single component glass is given by, for scattering is equal to 8 pi square divided by 3 lambda power 4 n square minus 1 2 kbtf bt. Here where n is a refractive index and kb is a Boltzmann constant and beta is a isothermal compressibility of materials, and Tf is a temperature at which density fluctuations are frozen in the glass as it is solidified. So another form of equation is, this is the equation of another form. So here is a P is a photoelastic coefficient. So it can be scattering loss for multi-component classes is given by mean square refractive index fluctuation volume of fibers. So multi-mode fibers have higher dopant concentrations and greater compositional fluctuation. The overall losses in the fibers are more as compared to single mode fibers. Linear scattering also occurs in the inhomogeneities, and these arise from the imperfections in the fiber geometry, irregularities in the refractive index, and the presence of bubbles etc. caused during manufacturing. Careful control of manufacturing process can reduce the Mie scattering to significant levels. These are the Mie scattering. So non-linear scattering losses, because of non-linear scattering, optical power from one mode to other modes is transferred is a forward or backward direction at different frequencies. So non-linear scattering losses are dependent on optical power density in the fiber. The non-linear scattering losses are more sufficient above power levels. Non-linear scattering effects are used to obtain an optical gain in the optical amplifier. Types of a non-linear scattering losses: stimulated Beryllium scattering, another is stimulated Raman scattering. Stimulated Beryllium scattering, SBS exists when light is modulated through the thermal molecular vibration within the fiber. The scattered light is absorbed as both upper and lower sideband separated from the incident light by modulation frequency. The optical power threshold for SBS is given by PB is equal to 4.4 into 10 power minus 3 d square lambda square alpha dB velocity into watts. D is a fiber core diameter, lambda is a operating wavelength, and alpha dB is a fiber attenuation, and V is a source bandwidth. Stimulated Raman scattering, SRS, is stimulated with the high frequency optical photon generated in scattering phenomena. SRS may exist both in forward and backward direction in optical fibers. The optical power threshold is 3 times higher than the SBS threshold. Threshold optical power SRS is given by PR is equal to 5.9 into 10 power minus 2 T square lambda square alpha, that is fiber attenuations, watts. Review questions. Explain scattering losses of an optical fiber with the neat diagram and expressions. Attenuation encountered in optical fiber communication due scattering. I hope that, dear students, all of you understood about the scattering losses. Thank you.